So I wasn't recording, so while you're writing it, I'm just going to repeat what I said. So on slide 13, not the homework, but slide 13 of the PowerPoint, we have a situation of rolling 2 dice, and we're looking at the sample space. Let's recall what the sample space is. The sample space is a collection of all possible outcomes. Now, if you're playing a game like Monopoly or something, you don't really care about the actual outcomes. What you care about is the sum of the 2 numbers, right? So we're not talking about a sample space where you're looking at 2 through 12 as the sum of the 2 number outcomes. Rather, we're going 1 layer lower or 1 layer deeper, where we're looking at the actual 36 outcomes themselves. So a 1 and a 1, 1 on the first day, 1 on the second die, 1 and 2, 1, 3, 1, 4, 1, 5, 1, 6, all the way through 6 and 6. That's the table. So the first question is, are the 36 outcomes equally likely? Is any one of those 36 outcomes more or less likely than any of the other 36 outcomes?
So yes, they're all equally likely.
Yes, they are all equally likely. Assuming it's 2 fair dice, which we are assuming, it makes no difference which die each side is as equally likely as anyone else. So those 36 are all equally likely. But the question is, what is the probability of rolling a doubles?
1/6.
So how do you get that?
Because there's 6 outcomes, 1, 1, 2, 2, 3, 3, and so on. And there's 6 of those, and then 6 over 36, and then I just went to the lowest.
Excellent. Because remember, when it comes time for computing the probability of an event that has equally likely outcomes, and this is why it's important that they're equally likely, we take the number of situations that give us what we're looking for. In this case, doubles. There are 6 situations that give us doubles. And we divide it by the number of total possible outcomes. In this case, there's 36 possible outcomes. We actually wrote them all out. So we know there's 36 possible outcomes. So the probability of rolling a doubles is 6 over 36, which then reduces to 1/6. Does that make sense? Okay. Then it says, find the probability of rolling a sum of 7 or a sum of 11, which means what we're looking for in this problem, you can't get a 7 and an 11 simultaneously. They're not asking for that. They're looking for the probability of a 7 or an 11. So we're going to look up all the ways. We're going to go through the table, and we're going to identify how many of those 36 outcomes give us a 7 as a sum or an 11.
6 for rolling a 7 and 2 for rolling an 11.
8 out of 36.
So what was it again, Megan?
It's 6 out of 36 and then 2 out of 36 for 11.
So the question I ask again, I'm looking for one answer, which is, what is the probability of rolling a 7 or an 11?
8 out of 36.
Excellent. 8 out of 36. Because I'm not looking at the 6 or the 7 or the 11 individually. Mm-hmm. I'm happy with either one. Anyone know a game where you might be happy with a 7 or an 11?
Craps tables.
Exactly. Now, I'm not saying you should go to Vegas and lose all your money like I did, but if you were to actually play craps, then getting a 7 or 11 at certain times would actually be a good thing to do. And you might be interested in knowing, okay, well, how much do I want to bet given the fact that I only have an 8 out of 36 chance of getting what I'm looking for? 8 out of 36 is 4 out of 18. 4 out of 18 is 2 out of 9. And 2 out of 9 is 22% approximately. And so, 1 in 5, 1 in 4. These are the things that you can calculate to decide whether or not you would like to take risky ventures. Anyway.
Professor, I have a question.
Yeah, go ahead.
So when you see words like or, we can assume that it means and, right?
Well, no. If you see or, you can't see and. They're 2 totally different things. Think about it. What is the probability of getting a 7 and an 11? On one roll,
No probability.
It's 0, right? You can't get 7 and an 11,
Okay.
right? It's impossible. It's either one or the other, or neither, right? So,
Right.
so and implies that both of them happen simultaneously, and or implies that you're happy with one, you're happy with the other. I really don't care which one it is.
Okay. All right.
Now,
That makes sense. Yeah.
if you're asking about the math, what do we do with an or an and situation with the math? That's something else, and we'll get to that. Okay, but right now, we're not really developing more complicated mathematical approaches. We're doing it the brute force, simplest way, which is actually writing out all possibilities and straight up counting them. Does that make sense?
Right. Yeah.
Okay. So now on the next slide, and this is, we're almost done with this PDF. The next slide, it says construct a probability distribution table for the sum of 2 dice. So remember what a probability distribution table means. It means you're going to first write in a column all possible outcomes. And then on the next column, you're going to write how probable those outcomes are. Now, in the situation of rolling 2 dice, what is the smallest possible numerical outcome?
2.
2, right?
1, 2.
2. 2. Snake eyes. 2.
I don't think you can roll a 1 with 2 dice. That will be quite the feat. So when we make our first column, the first number, the lowest number is going to be 2. Now, can you get a 3 if you roll 2 dice?
Yeah.
How about a 4?
Yes.
How about 5, 6, 7, right? You write all
To
the
be up to 12.
Up to 12, right? You can't get any higher than 12 with 2 dice. So you write out all 11 possibilities, 2 through 12.
Sorry, Professor, is this for slide 14?
This is slide 14, correct?
Okay.
Okay, so now the question is, what is the probability distribution? Are these 11 outcomes, 2 through 12, equally likely? Well,
Is
let's
it
see.
probability distribution?
Probability distribution. That's when you list all the outcomes and you list how probable each of them are. So let's go to the first one, which is rolling a 2. How probable is it to roll a 2?
Is that 1 out of 36?
1 out of 36. There's only one way to roll a 2. You have to get 2 ones. There's no other way of rolling a 2. All right, so the first one is 1 out of 36. How probable is rolling a 3?
2.
2 out of 36.
2 out of 36. You can't just say 2, that's too big, but 2 out of
Right.
36,
That's
right?
2 out of 36.
How about the probability of rolling a 4, of rolling a 5, of rolling a 6, 7, 8, 9, 10, 11, 12? Write them out based upon the table. And you should notice a little pattern as you do this, by the way.
Mm-hmm.
As you go through the table, you should notice a pattern that should help you quickly determine these probabilities.
Wait, I'm a bit confused.
Yeah.
Can we
same.
go over that again, please? Sorry.
Sure, which part?
Yeah, distribution table. Like, how do we do that again? I'm sorry. It's just
No,
been a
don't
little.
apologize. It's okay. A probability distribution table is 2 columns. The first column are all of the outcomes. So when you're looking for the sum of 2 dice, what are the outcomes? What's the lowest thing you can get when you add 2 dice? The smallest number is 2. 2 ones, right? Correct?
Yes.
See who's asking? Okay, so the smallest one is 2. And then 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. You're going to write 11 numbers, one after the other in a column. The next,
Up to 12.
up to 12. That's the highest number you can get, right?
Mm-hmm.
Now the next number, the second column, are the actual probabilities. How likely is it that you get those numbers? How likely is it to get a 2 or a 3 or a 4 and so on? So since the 36 actual outcomes are equally likely, we can just count up. How many ways can you get a 2? And that's over 36. So how many ways can you get a 2 out of 36?
Well, Professor, this might be a dumb question, and we
Yeah.
might have already talked about this.
It's okay.
I was trying to print out these slides, but why are we doing it out of 36?
There's 36 outcomes, aren't there?
Four.
Not.
I don't see how we get the.
Well, look back at the previous slide. We had a table of 36 dice rolls. One,
Okay,
one,
we're
two,
still
one,
going
three.
through. Okay.
Yeah. That's still. It's
That's
the
why I was like,
same.
it's probably a dumb question.
No,
I didn't
no.
know we were still going off of.
Okay, it's the same two dice,
Okay.
right? It's the same two dice. It's just we're looking at something different. We're not looking for doubles. We're not looking for 7 or 11. We're looking for each number. How likely is it to get a 2? There's one way of getting a 2 out of 36 outcomes, right? Only way to get a 2 is 1, 1. That's it.
Right.
No other way of getting a 2. Then the question is, how likely is it to get a 3?
Would be a 1 and a 2, or a 2 and a 1, which is 3 out of.
No, that's 2 out of 36.
Or 2 out of 36. I meant.
Right,
Yeah.
there's still 2 out of 36, which can reduce to 1 out of 18, but 2 out of 36 is fine.
Okay.
And
So
how many
4.
ways? Huh?
So we're going to 4 now. It would be either 2 and 2, or 2 and 1, and a 1 and 2.
Wait. 2 and 2 or 2 and 1? Did you
2
say?
and 2, 2 and 2, 3 and 1, and then 1 and 3.
So how many possibilities is that?
3 out of 36.
3 out of 36. Now, when you look at the table, tell me what little trick is asking for her meeting code and password.
It's in the. That's in the files.
That's in the files.
Yeah,
Someone's trying to get
on Canvas.
Okay,
You
so
gotta go to pages, and then it says Zoom code, and it has all the information there.
so this is in files, you said?
Yeah. Or you want me to put it in the chat? I can put the code in the chat.
Would you mind if would you mind doing that, please? That would be wonderful. That way she can pass it on. Someone said someone's trying to get in and is not able to. So that would be amazing if you don't mind.
That is
Just
the
to
code.
clarify,
Yes.
we count like each probability as 2 separate ones. If it's like 5 and 6 and 6 and 5, like
That's
those
right.
are 2 separate.
Right.
Yeah, because in terms of what can happen, those are 2 different situations. Getting a 5 on the first die and a 6 on the second die is completely distinct than getting a 5 on the second die and a 6 on the first die. It's if I said that correct. It's 2 different things whose end result is still getting an 11. You don't care which one's a 5 and which one's a 6. In fact, when you roll, you don't even remember which die is which. It goes too fast. But from a realistic standpoint, they are 2 different scenarios, and we count them twice.
Okay, thank you.
Okay. Did she get in?
I'm not sure. I put the code in the chat.
I made it in.
You made it in.
Yeah.
So what was the issue?
I don't know. I kept clicking the link from the email you sent last Monday to use, and it just kept saying that the host hadn't started the meeting.
Yeah, I had to use the Wednesday.
I
link,
think it
not
was
the
a
Monday.
new link that he sent on that Wednesday.
Yeah, I used the Wednesday link, not the Monday, because I tried Monday first.
It's the most recent sent out.
That's weird.
Is this the one for every week now, or?
So right now we have 1 for Monday and 1 for Wednesday, correct?
That's probably what my issue was. Okay.
That might be the issue. Okay. Thank you. Okay. So does that make sense so far?
Can I ask a question?
Yeah, of course.
I think you went over it, but like, I'm confused. Okay, so for the probability distribution table for the sum of 2 dice,
Yes.
why would it be 11 outcomes?
I'm sorry, say that again, please.
For like the first one, why would there be 11 outcomes?
There's not 11. Well, the 11 outcomes are 2 through 11 in terms of what the numbers can add up to. Right? I mean, if you roll 2 dice, what's the smallest number you could possibly get?
2,
2, right? And what's the next number you can possibly get?
3. Oh no,
And the one after that?
4.
And the one after that? 6, 7, 8, 9, 10, 11, 12, correct?
Mm-hmm.
For a total of how many?
2.
Well, there's 11 possible outcomes, 2 through 12.
No sum for 1. If you roll 2 dice, you can't get 1.
You can't get a 1, right? So the smallest one you can get is a 2, and then or a 3, or a 4, or a 5 to a 12. That's 11 possibilities for what you can get, right?
Yeah.
and that's why it's 11.
Okay, thank you.
But again, those 11 are not equally likely, right? Those
Right.
11,
So just moving possibility distribution. Just the thing I've noticed was it going up by 1 every time, right? So we're
well,
going like
up until
1.
7,
Right.
and then it starts
And
going
then it
down.
goes down. Yeah.
Right, which is why 7 is the most likely outcome. We can see why now. And if you've ever, played games, you might have noticed that certain numbers appear more than others. It's because there's more possible ways that can happen.
Mhm.
All right, 7 is much more likely to appear than anything else. Does that make sense?
Yeah.
So now it says, construct a probability distribution table for the larger number showing when you roll 2 dice. The
This is what I
lar-
had confusion with.
Okay, so this is
I
good.
didn't get this at all.
Okay, so let's go back to that same table that we've been working with until now. Okay, that same table. The first die, which is 1, 1. What's the larger of those two numbers?
They're equal.
Well, they're equal. So the larger one is just going to be the same as the smaller one, which is
1.
1.
1.
Okay, so 1 is a possibility for the larger of the two numbers. Let's go to the next one, which is 1, 2. What's the larger of those two numbers?
2.
2. So 2 is a possibility for the larger of the two numbers. Is 3 a possibility for the larger of the two numbers?
No.
Yeah.
No.
Sure, 1 and 3.
Oh, for the next.
Yeah, look at the chart.
Look at the chart. So just think about rolling 2 dice. If you roll 2 dice, is it possible that 3 is the larger of the 2?
Yes.
Is it possible that 4 is the larger of the 2?
Yes.
Is it possible that 5 is the larger of the 2?
Yes.
How about 6?
Yes.
How about 7?
No.
No. So the only numbers possible are 1 through 6. Now the question is, what is the probability that the larger of the two numbers is 1? Of the 36 outcomes that we have in our table, how many of them have a larger number of 1?
5.
Just 1.
Oh.
The only
okay.
one whose larger number is 1 is literally 1, 1. Any other one is going to have a bigger number, correct? So now let's go to 2. Of those 36 outcomes, how many of them have a larger number of 2?
Is it 2?
Well, tell me what those 2 are then.
Is it if you roll a 2-1 or a 2-2 because it says to count the doubles as a larger number?
Okay, is that it? Did you miss one?
Did I miss
I asked you first. So you said 2, 2, and 2, 1, right?
Yes.
Is there any other way the larger of the two numbers could be a 2?
A 1 and 2?
How about a 1, 2?
Yeah. Okay.
Right? So how many of the 36 ways will give me a larger number of as a 2?
3 out of 36.
3 out of 36. So the probability for a 2 is 3 out of 36. Next, how many ways can the larger of the two numbers be a 3?
5.
5.
Whoa.
You see a pattern yet?
Yeah, it's the pattern it's making on the chart.
Yeah, so what's the pattern, right? This is the beautiful thing about math, right? We look for, yes, excellent. We look for patterns. And then once you see patterns, you can do things a lot quicker than you would by actually computing them. So the pattern is, as Megan just pointed out, you have the top corner, and then you make a little half square, the next, and then the next, and then the next, and then the next, and then the next, and you get the whole thing.
Excuse me, Professor.
Yes.
I'm sorry, I'm like kind of getting lost.
Sure.
Going pretty fast. Like,
yes.
Are you able to write this down so I can visually see it? Because I feel like
that.
Yes, I second that.
Yeah.
So I got my whiteboard up. Can you see my whiteboard?
Yeah, thank you.
You keep saying that.
Huh?
I was thinking
it, right?
Tatiana.
Is it clear?
If you have it right,
Yes.
Sorry, I can't hear you guys.
Yes, kind
Yes,
of.
you're good. I can see it.
Okay. So let's look at just this part here. It goes on. There's more. There's more. There's more. There's more. There's more. But this is the beginning of the table, correct?
Yes.
Okay. So the top left one over there. Oh, I'm gonna make my picture bigger to confirm that you guys can see it well, because it seems kind of small on my end. I don't know how to zoom in on mine, but you said you can see it, so I'll trust you. The top one there says what?
1, 1.
1, 1.
What's the bigger number between 1 and 1? The bigger number is just 1, right?
1.
The bigger number is 1. It's the smaller number. It's just a number. So this one corresponds to the number 1. What's the bigger number here?
2.
2. So this corresponds to a 2. How about this one?
2.
2. How about this one?
2.
2. If I go to 3, 1, what's the bigger number here?
3.
3. So the question is, what's the probability of having a larger number of 1? Well, the only way to get a larger number of 1 is that one. Correct?
Mm-hmm.
But to get a larger number of 2, we have any of those 3 possibilities. Do you agree? And then to get a larger number of 3, we go to the next, because we have 1, 3, 1, 3, 2, 3, 3, 2, 3, and 1, 3, all would have a larger number of 3.
Can you, sorry.
Yeah.
Maybe I'm just not understanding that part. But
Okay, okay.
you're saying to get a larger number of 2, you're only going to be looking at those 3 numbers?
Well,
or those 3 possibilities?
Well, yeah, because give me a possibility from somewhere else.
Got it.
Give me a possibility from somewhere else. How about 5, 4? Does 5, 4 have a larger number of 3?
No, it doesn't.
Yeah.
No, it has a larger number of 5, right?
Mm-hmm.
Okay.
So once you get past the next little L shape, right? Once you get past the next L shape, then how can the bigger number be 3? Can you zoom in? I can't see it. I'm sorry. I got a text I just saw. The person who sent me something again if it's clear or you still need explanation.
No, you're good. You're good.
I got it. Well, you weren't the one who sent it to me though, so.
Oh, sorry. I thought you were asking me.
I have Van Stations 2 iPhone. So Van Station 2 iPhone, is there still a question? Zoom in, I can't see the board.
How would you write it in the table?
How's that?
This is fine.
How would I write in a table? Hi, Nabira. Okay. How would I write in a table? Well, you don't do it in a table. The table are the you mean the 6x6 table? Is that what you mean?
Yeah.
Is that what you mean? Well, the 6x6 table are the actual outcomes. We're listing it in a column now.
No, how does the distribution table look for that?
Yeah. So okay. So the distribution table, the first column, are going to be all the possible values. What are all the possible values? Oh, there it is. Wonderful.
Yeah.
So look at Molly's page. Can you all see Molly's? I don't know if I can zoom. I don't know how to zoom in on.
Can she show it again? Just a little bit closer.
Molly is showing it. She's doing great. I just don't know how to. I don't know how to maximize her screen. Is there?
You go to the 3 dots and then you pin her video, or you like showcase her video.
If you hover.
Spotlight video. Got it. Okay, so that's
mine looks totally different.
So that's wonderful, right? What do we have? We have all the possible outcomes, 1 through 6, with their corresponding likelihoods of occurrences.
I see.
Getting a 1 is a 1 out of 36 probability. Getting a 2, 3 out of 36. Getting a 3, 5 out of 36, and so on. So you can actually kind of make your own games like this. You can make games with like something like if the maximum number is 1, I get $1 or 2 or 3 or something like that to make money, lose money. Of course, you're talking about a degenerate gambler here. So, anyways, let's go back to cancel the spotlight video. So now we're back to me. Oh, look at this. So does that make
Can
sense?
Molly hold it up just one more time?
Can
sorry.
Molly hold it up just one more time? I'm sure. I hope she doesn't mind.
I'm sorry, Molly.
It's okay. Hold on. I gotta. Okay, hers is up.
It's in the chat.
Is that good?
Okay.
Oh,
Yeah.
I'm covering it up somewhat. I'm sorry.
I mean,
Is that good?
You're good. I'll
Okay.
figure it out
It's
somehow.
good. So now I'm going to go back to spotlighting me. Okay. So, and by the way, look at the question on the slide. It says if they are the same, just use that as the larger number, right? So they actually said specifically what to do in that situation. So now we have the third question, which is what is the most likely sum? Now this is not dealing with what we just did, which was the largest number. This is dealing with the sum, the question that came before it. What is the most likely sum in this situation?
7.
Sum of 7.
Seven. Okay. And what is the least likely larger number? So now let's go to the new situation. The questions are kind of all over the place, but what is the least likely of the larger number?
A 1.
A 1. A 1. Does that make sense?
Mm-hmm.
So this takes us to the end of the first chapter.
Okay, I figured out that.
Questions on the first chapter?
No questions on the first chapter, but like now that we finished it for homework, is it like due by next class?
No,
or-
you'll have a week. So it'll be due on well, next Monday is Labor Day.
Okay.
We don't have class Labor Day, do we?
No.
Unless everyone just agrees to meet anyways because math is so fun. Is that the case? I don't know if you guys feel the same way about math as I do. Maybe you do. Maybe you want to meet 7 days a week. I don't know. But I'm gonna go on the assumption thrown out there that we're not meeting Monday. In which case, both the first homework and the first quiz will be yeah. So here's what we're gonna do. The first quiz on the first chapter and homework will be Wednesday, not Labor Day, but Wednesday. I am going to base the quiz on the homework. I'm going to post the solutions to the homework Monday, a week from today. Okay, so that you'll have a week to work on them with no solutions. And then you'll have 2 days if you want to look at them with the solutions. Why is the most likely sum 7? Well, look at your probability distribution for sums. Which had the highest probability?
I have a question.
Well, hold on. Let me answer her question first. This is Karen's question. Karen, when you look at those, the probability distribution, what's the value that we have for 7 versus all the other ones?
I don't get it. Sorry.
No, it's okay. Do you have your distribution in front of you?
Yes, I do.
Okay, so what number do you have by 7?
4?
Mm.
Wait,
What do you mean 4?
wait, which 7?
Um,
What do you mean by 7?
I'm sorry, I'm having a hard time hearing you. Let me turn a little louder. 1 second.
What do you mean by 7? And like, it's the sum of 7. Every outcome that adds up to the number of 7 is what I mean.
Yeah, how many ways can you have the 2 dice add up to the number 7?
Okay, I get it now.
And then we divide each of those by 36 because we want a probability. Okay, so anyway, so someone had mentioned they had a question. I'm sorry, I was answering hers, but what was the question?
I had a question. If we have questions on the homework, when should we ask you? Today or Monday?
Well, not today because I don't want to answer questions before everyone has done them. I want people the opportunity to try them themselves.
We aren't going to review the homework before we take the quiz then?
So what I can do is as follows. This is what my thought was. On Monday of next week, I post, and tell me what you think about this. On Monday of next week, I post the solutions. Beginning of class on Wednesday, I answer questions that people have on them, and then we go into the quiz.
Okay, that works.
Okay, and then now I can't answer every question. So there is going to be a cutoff of, let's say, 15 to 20 minutes into class and saying, okay, we have to start now. So don't just say, oh, I'll just get everything in class, because unfortunately that can't happen.
How will the quiz work?
Yeah.
Is it on Canvas?
The question?
The quiz?
I can certainly post it on Canvas. Well, you want me to post it outside of class time? Well, I can't.
Well, how are we going to do the quiz?
Will be administering it online? Like, will we take it through Canvas?
That's a wonderful question, and I haven't thought about it yet. Yeah, no, it could be done on Canvas, whether in class or out of class. It could be done. It could be done by hand, and then you scan it, or email me let me think about it. I don't know yet how I want to do it.
A nightmare.
Yeah, it's not the easiest situation.
Mm-hmm.
Unfortunately, but it is what we're working with, and we're just trying to make the best of it and trying to make it work. Do we have to write the answers for the quiz in complete sentences? Well, if I ask for a probability, like calculate the likelihood, you say 3/7, that's fine. But if I ask for something that requires a context or a complete sentence, I would expect a complete sentence solution.
And when will the quiz be?
I'm sorry?
When will the quiz be?
Next Wednesday.
Yeah,
Okay.
Wednesday night.
Next Wednesday.
Because we don't have really a schedule when the quizzes will be.
Oh, no, but I mentioned it a few minutes ago that it'll be Wednesday.
Yeah.
Yeah, no, so I'm not making a schedule for when the quizzes are, because I can't give a quiz until we, finish.
Okay. Yes,
and we fall behind.
That makes sense.
So for me to just schedule quizzes for the whole semester would be, I'd be changing things left and right. So the easiest way is just schedule them as we're ready for them.
Yes.
Okay. All right. So let me now share.
So I have a question before we move on.
Yes, go ahead.
I know I've been asking lots of questions, but
I don't mind lots of questions.
Okay, I thought I'd just try to figure out on my own. I'm just having trouble understanding where you're getting what it actually means when you're talking about like larger numbers. So you know how we did the constructor probability table showing.
So look at two numbers. Like if I roll a 4 and a 5,
right?
Which is literally the larger number?
5.
That's it.
Okay, so when we're doing that table, though, we're putting the number on the left side of that table, 1 through 6.
Well, any probability distribution will always be the same. All possible answers on the left, and their probabilities on the right. So if you roll a 4 and a 5, the larger number is the 5, correct?
Right.
So 5 is a possibility for when all I care about is the larger number. So that's going to go on the left.
Okay.
And if I roll a 1 and a 6, what's the larger number?
The 6.
So 6 is a possibility. It goes on the left. So all possibilities go on the left. What's the smallest possibility for which is the larger number?
The spot would be the other.
I'm sorry?
That's
I'm asking you for concrete. I want to know, for this example of rolling 2 dice, what is literally the smallest possible number that could be construed as the larger number when I roll 2 dice?
1.
So a 2.
Oh, I'm so sorry.
It's okay. It seems like it's a very cute dog. No,
it's not.
So a 2, if I roll a 1 and a 2, what's the larger number?
A 2.
A 2. So 2 is certainly a possibility for when I care about the larger number. But if I roll a 1 and a 1, the problem specifically says that if you roll doubles, just count that as the larger number. The problem specifically says it in the problem. So if I roll a 1 and a 1, what's the larger number?
A 1.
A 1. So 1 is also a possibility. So what I'm doing is I'm writing out all of the possibilities. The possibilities are 1 through 6. That's the left side of my table. Those are the possibilities. And then the right side of the table is how likely it is to be a 1, to be a 2, to be a 3, to be a 4, to be a 5, and to be a 6. And that's when this thing plays a role here. Yes? No? Maybe so?
No, yeah. I'm starting to understand it more.
A little more.
I just have to. Yeah, I'm good.
Like everything else, there's nothing wrong with going over things.
Okay.
Okay. So now let me.
I have one quick question
Yes,
because
go
I
ahead.
slipped in just as you answered this question.
Yes.
For the one that says find the probability of rolling a sum of 7 or a sum of 11, how would it be 2 answers or would it be a combined answer?
It would be a combined answer.
Combined answer. Okay.
It would be a combined answer.
Will you be posting the next slides on Canvas?
I'm doing it right now.
Mom, I literally, can you put the dogs away?
Who let the dogs out is the question. So desktop simulation chapter 2. Let me now go to Canvas and post it immediately as we're talking. So file, see, it's if I say I'll do it later, then I'll never do it. So, or it'll take me forever. I just know myself. So what I'm going to do here is find the link that I just created. Here it is, and we're going to upload it. And chapter 2 is now uploading. Let's give it a second to upload completely. And then we will be ready. Okay, it's up there. Yeah, it's up there. Do you all see it?
Mm-hmm.
Okay, so chapter 2 is up. Chapter 2 is labeled as simulation. Simulation. What is a simulation? A simulation is when you don't do the exact thing that you're trying to do, but you do something else which is just as good. Here's an example. If I ask you to pick a random number from 1 to 10, okay, if I say pick a random number from 1 to 10, what's one way of doing it? That would be to just say a number between 1 and 10, right? 7, 3, 5, 2, 0. Well, no, 0 is not between 1 and 10. That was stupid. But you know what I'm saying, right? I can simulate this.
Question, Professor.
Yes, go ahead.
Where's the slides and the notes for this one?
I just uploaded to files. You don't see it? Does anyone see it?
You just have to
Yes,
wait.
it's up.
Yeah, I got it up
You
right
see
now.
it.
It might take a couple minutes to process sometimes, but it should be up.
Okay, thank you.
Okay. So
Okay, thank you.
so a simulation is, so if I well, rather than me trying to come up with a great situation, let's actually just go through it, and you'll see even better ones. Okay. So simulation using physical objects. A simulation is a method of estimating a probability empirically by using a device that generates outcomes with the same probabilities as the actual chance situation. In other words, if I say I want you to pick, if I want you to pick a card from a deck of 52 cards at random, right now I want you to do it, you would most likely say, well, I don't have a deck of cards handy, or they're in another room, or I'm just too lazy to get up, or I don't care, I don't want to do this anyway. You'll say something along the lines of, I don't have a deck of cards right now. But I say, no, you got to do it. You got to give me a random card from a deck of cards. And you're like, I don't have a deck of cards. What am I supposed to do? I say, well, we can simulate it. We can do a different situation that gets the same result across. What's a possibility? Well, what I can do is I can label every card in a deck from 1 to 52, put 52 little pieces of paper with 52 numbers on it in a hat, take the hat around, pull out a number, and whatever number it is, that corresponds to the card. Was that essentially the same thing as actually picking a card? Did it get the same result across? The answer is yes, it's perfectly valid. I have simulated picking a card by doing something else instead. That is what a simulation is when you do something instead of the actual thing that you're doing. These words are very vague. Oh, look at the cat. Anyways, you do something to basically, you don't want to do one thing, but you need its results. So you do something simpler, and you're perfectly happy. That's what we're doing with simulations. So if we look at the first slide, in elementary school, simulation is done using physical objects where the probabilities are known, the outcomes have known probabilities, such as spinners, dice, cards, and coins. Okay, those are the types of situations that we're going to be dealing with. So anytime I ask you for an example of something, and you say, oh, the Super Bowl or this, don't use real life. Real life is complicated. Use simple examples: dice, coins, cards, spinners. Very, very straightforward, that anyone could really wrap their heads around without having to worry about real life situations. So if you look at the second slide, example. According to the High School Youth Risk Behavior Survey, 1/3 of Los Angeles Unified School District high school students reports that they have tried cigarette smoking. 1 out of 3. If I pick 12 students randomly, and I'm interested in counting how many of those 12 students smoked cigarettes, I would actually have to go out and find 12 students and do that, right? Well, I don't want to do that because I'm scared of LA Unified students, okay? I don't want to deal with them. They frighten me. So how can I simulate this situation without ever actually having to deal with students? So what I can do is simple. I can take a quarter and say, this flip will be the first student that I find. If it's heads, they smoke cigarettes. If it's tails, they don't. The problem with that, of course, is that's 50-50. That was a bad example. I don't want a 50-50. I want a 1/3 possibility. So how can I find something that has something simple that has a 1/3 possibility of occurring? And again, think of dice, coins, cards, spinners. Give me an example from those of an event that has a 1/3 chance of occurring. I'm sorry, you're going in and out. I can't hear you.
A spinner with 3 colors, and if you land on a certain color, then you've tried cigarette smoke.
Okay, so that's wonderful if and only if what is true about that spinner which you have not specified.
There has to be 3 colors.
Well,
they have to be equal in size.
So hopefully I have the following. Hopefully you can see this. So here's my circle. Here's black. Here's green, and the rest is yellow. There's 3 colors, right? But they're not equal in size. So you're not as likely to land on those other 2 colors, right? So your example was great, but you have to be a little more specific. Okay, so that's a possibility with spinners. Can we come up a possibility with dice for a 1 in 3 possibility?
I want to say at least 3 dice. 3
die. How about just 1 die? How about just 1 die? Can we come up with a possibility?
Oh.
With 1 die.
Of getting an odd number?
I'm sorry?
Of getting an odd number?
Getting an odd number would be 50%. We want a 1/3.
Prime number.
Prime number is also 50%. 2, 3, and 5. Yeah, shit, right? That didn't work either. So give me something that works. We want a 1 in 3 chance with rolling a die. And don't use my language in 6th grade or lower classes. It doesn't work out well. So give me something with dice that's 1 in 3.
Oh, what if the die lands between like 1 and 2 or 3 and 4 or 5 and 6?
All right. So if it lands 1 or 2, we'll call that smoking. And if it lands 3, 4, 5, 6, we'll call that non-smoking. Right? Is that 1 in 3?
Isn't that not even?
Why is it not even? There's six equally likely outcomes.
There's only 2.
If you're giving the smoking option 2 out of the 1 and 2, but then you have 3, 4, 5, 6 or not. Why are you giving the not more
Because smoking is only a one. Because smoking's only a 1 in 3 chance. It's not a 1 in 2 chance, right? The data suggests that that 1 in 3 people smoke. That's the same thing as 2 in 6 people smoke. Correct?
Right. Okay.
So if the data is 2 in 6, we want a situation where 2 out of 6, I would say, smoke, and 4 out of 6, I would say, don't smoke. Correct? Agreed?
That makes sense. Yeah.
Okay. How about something with cards? Can we come up with a situation with cards?
Oh man, playing cards.
Yeah, playing cards. Can we come up with a situation with playing cards for a 1 in 3 chance? This one's a little tougher to think of, but let's see if anyone can get it. Can we come up with a situation with cards where we want a 1 in 3 chance?
Can you use an ace, a 2, and a 3 and have a person pick one of the cards?
Yeah, you don't exactly. You don't need all 52 cards. Just take 3 cards out, and we'll say ace is for smokers and 2 and 3 are for non-smokers.
Oh, okay. That's
right?
awesome.
And just pick randomly one of the 3 cards. Correct? That's a wonderful, whoever said that. It's a wonderful example, right? You don't need to use all 52 cards. Why make it more complicated? Right? Just take 3 cards out. 3 cards is 1 in 3. Just got to make sure that we know which one is which, of course. Agreed?
Mm-hmm.
So in this example on the slide, it says match outcomes on the spinner to the actual outcomes. So we want to draw and label sectors on the spinner so that it can be used to model asking one randomly selected student or if he or she has tried cigarette smoking. So that was our first example. We divided to 3 sections of equal size, and one of the labels we label as smoking and the other 2 we label as non-smoking, and then we spin it. And if it lands in smoking, that student that we asked is a smoker. And you know what? It's just as good at going out there and actually taking a poll. It's a simulation. It got the same results without doing the actual activity. We simulated it. Does that seem reasonable and make sense? Okay.
Yes.
Now, it says in the next part, it says, repeat this until you have completed 1 run of the simulation. 1 run of the simulation is doing it 12 times. Because the question is, if I ask 12 students, how many of them smoke? That's a run. Go through it 12 times. So let's say I get 5 cigarette smokers. So that's a 5 in 12 chance. That's pretty close to what the LA Unified suggests. It's 4 in 12. Right? 1 in 3, 4 in 12, same thing, correct? Now I can do the simulation 1,000,000 times. In fact, just so you know, I had a internship this summer, and one of the things that I had to do was write a program where I had to run the program 10,000 times and then work with the answers and yada, yada, yada. It gets a lot more complicated. But I did exactly this. I ran a simulation a lot of times, and then I analyzed the data. That's what you do in statistics. And it can be fun. Personally, I hated it. But, you know, everyone's different. You know, it's just some people like this crap. What can I say? I didn't, but hey, next person might. Anyways, so after asking all students using the spinner, what should you record? What do we actually care about? Do we care about smoker, smoker, non-smoker, non-smoker, smoker, non-smoker? Do we care about the actual values for each spin? Or do we just care about the total that we get after all 12?
The total that we get.
The total that we get, right? So every time you do a problem, you have to ask yourself, what do I care about? Do I need this data? Or do I need just some kind of summary of the answers? In this case, it's a summary that counts. So the next slide, it says, describe how you could use dice to conduct 1 run. We already talked about that. Describe how you could use a deck of cards. We talked about that. So let's go now to the next slide, which is slide 4, class activity. Are we all together so far? Seems okay, no major complaints or anything like that? Okay. About half of all kindergartners are girls and half are boys. Now, let's say you're a teacher and your principal or whatever comes to you during the summer and says, okay, we have a class for you next year. You're going to love it. We have 15 children. It's going to be fantastic. And you go, 15, I wonder how many boys and girls I'm going to have. Well, of course, if they give you the roster, then you can check, assuming that, of course, it's obvious names to gender. Sometimes it's not. Bobby, for example, could be either one. And of course, you know, with gender fluidity, you never know. But let's say, again, this is for children. We're not looking at complications. Let's say we just have 15 children, boys and girls, without any gender fluidity issues or anything that might confuse the simplicity of just two possible outcomes. Not that it's a real thing, I understand that, but just in terms of simplicity. So you're asked, you're going to have 15 children. The question is, how can you simulate how many boys or girls that you're going to have in the class? What can you do to simulate something with a 50% chance or a 50% chance?
It's the coin, right?
Oh yeah,
coin 15 times.
Yeah, exactly. Flip a coin 15 times. Every head is going to be a boy, let's say. Every tail is going to be a girl, or vice versa. It makes no difference. It's your choice. One's as equally valid as the next. And then, you know, however many boys and girls you have, that's a simulation right there, and you're done. It's you know, it's very straightforward. How about using a die? How would I simulate a 50% probability with dice? 1 die, 2 dice, 10 dice, however many you want to use. You have as many dice as you want. How would you simulate a situation of 50% with dice?
All the odd numbers are boys, all the evens are girls?
Perfect. Odds boys, evens girls, or vice versa. Odds primes, even non-primes, or all right, that makes sense. Primes boys and non-primes girls, or vice versa. 1, 2, and 6 boys. 2, 3, and 5, or 2, 3, 4, and 5 girls. You can do whatever you want. It's up to you. Of course, why complicate things? There's no need for it, but in theory, you could. These are all perfectly valid. Does that make sense?
Yes.
Okay, so on page 5, it actually asks you to do a run. It actually asks you to take out a coin or a spinner or a die or a deck of cards, if you can come up with a way of doing it with cards, or anything with 50-50, and actually go through it. Okay, now here's what we're going to do. If you look at this table, it has 0 to 15. Correct? 0 to 15 what?
Boys.
Okay, it could be boys, it could be girls. It's up to you, unless they specifically say. They don't specifically say. Let's say it does say top left corner. I missed it. Number of boys. They actually did say. I'm sorry. Number of boys. So it could be 0 through 15. So if I do 1,000 runs of this, 1,000 times I do this, and I put my tally of how many times I got 0 boys and how many times I got 1 boy and 2 boys and 3 boys and 4, all the way through 15. Which ones do I think are going to be amongst the largest numbers? Do I think I'm going to have 0 boys a lot of times?
No.
Probably not, right? Because if it's 50-50 to get 0 boys, it's pretty rare, wouldn't you say? How about 15 girls and either 0 boys or 15 boys? Both of those don't seem very common. Have you ever seen a kindergartner class with no boys or no girls in it, unless it's a school, you know, non-co-ed or something like that? Probably not. So where do you expect the highest likelihood to be?
6 and 7.
Yes, or 7 or 8, right? Somewhere in the middle, correct? So if you actually did this, you should expect to see numbers that go up from 0 to 7 or 8 and then go down again on the other side. That's what you would expect. So let's say you filled out this table, you did it 1,000 times, and let's say 12 of those times you had 0 boys. Out of the 1,000 trials, 12 times you had 0 boys. So let's fill in 12 just as a number for 0. The question is, what is the probability? What is the probability that's right beneath it? What is the estimated probability based upon your simulation? What is the estimated probability of having 0 boys?
12 out of 1,000?
Awesome. 12 out of 1,000. Right? It happened 12 times. There's 1,000 possibilities. 12 out of 1,000 is our answer. And you can do something similar for each column. But tell me what the two last columns would have to be for total. If I did 1,000 simulations, what is the top right answer going to be for total?
Does it have to be 1,000?
Well, if the top line is how many times each of them occurred, and you did 1,000 simulations, then yes, the top one has to be 1,000. What does the bottom one has to be? Have to be.
Also 1,000?
No, the total one is
Half.
how much? What do you say it was?
Oh, I said at least half.
No.
I said 5. No? Okay.
What was that?
Is it 1?
It's 1.
Because it's 100%.
You have to add to 100%. You're adding up all probabilities, correct? You're adding up
Okay.
all the probabilities. They have to add to 100%. So the top right corner is the number of simulations you ran, but the bottom right corner has to be 1. I can fill that out right now without ever doing anything. Everything else depends upon you, but the bottom right corner better be 1.
That is because we're doing the probabilities as fractions, and over time, after the 1,000 trials, all those fractions have to add up to 100%, right?
That's right. And even if they were decimals, they would have to add up to 100%. It doesn't make a difference if it's fractions or decimals. Now remember, if you round because your calculator has too many decimals, then it might not look like 100% because you're adding rounded numbers, but it really is 100%. Does that make sense?
Mm-hmm.
You know, if your calculator rounds a little bit, and at the end, your number might be a little off, but it really is 100%.
I'm sorry, are we still on slide 5?
Yes, we are.
Because I'm like confused. So for like you said, for this frequency, we're putting 0 all the way up to 12?
15. Why 12?
I heard 12 too.
For 12?
Well, you're saying that like 0, like if we got 0 boys.
No. What I said was, as an example of a possibility, what if you did 1,000 simulations and 0 occurred 12 times? Right? What if you looked at 1,000 classrooms in America of kindergarten children that had exactly 15 children, and 12 of those classes had 0 boys. That's a number of times 0 occurred.
So this is like a whole different example from what we're
What do you mean?
Yeah, I'm kind of confused. So your estimated probability at the bottom, your bottom chart.
Yeah.
Would those, like if it was 0 out of 12 or 1 out of whatever, those the denominator would have to add up at the end of your 15 would have to add up to 1,000.
Okay. Yes, but let me recap because there's a little confusion. Let's assume that you ran 1,000 simulations.
Right.
Every simulation was 15 tosses of a coin. So the first time you tossed 50, so you took 15 coins out of the bag and you tossed all 15 of them, and you counted how many heads there were, and you got 9 heads. This is simulating a classroom in America with 15 children that had 9 boys. Okay, we're not actually finding a classroom, we're simulating it. We're pretending.
And that would be one
That would be 1 tally under the 9 mark.
Okay.
Right? And then we do it again. And then we do it again. And then we do it again. And we do it 1,000 times. And my example was, suppose after the 1,000 simulations, you had 0 boys precisely 12 times. So the number 12 should go under the 0.
Okay. And then your estimated probability
for getting 0 would then be 12 out of 1,000.
Okay, now
because of those 1,000 trials, 12 of them gave you 0. So the probability of getting a 0, according to my estimation, is 12 out of 1,000. And then I would count how many times 1 occurred over 1,000, 2 over 1,000, and so on, all the way to 15. Does that make sense?
So the question, for B, it's saying individually conduct 1 run.
Yes, so individually conduct 1 run, and then record your result and those from the rest of your class in this table. So this table represents lots of runs. we only have 45 people in my class, but I wanted a larger number. I picked 1,000, supposedly a class of 1,000. This table would represent all 1,000 of our runs, or all 1,000 of your runs if you want to do it alone 1,000 times. Let's say you're really bored one night and you have 15 quarters and you're like, you know what? I'm going to run the simulation 1,000 times. So you flip all 15, you see 9 heads, you put a mark by the 9. You collect all the coins, you do it again. Now you have 7 heads, you put a mark by the 7. Then you collect all the coins, you do it again. Now you have 11 heads, you put a mark by the 11. And you do this thing 1,000 times. The top row represents how many times you got each number. What's the total in the top right? 1,000, because you ran 1,000 simulations. The bottom row is how likely each of those numbers are. So how likely is it that I got a 0? Well, 12 out of 1,000, because it happened 12 times. How likely is it that I got a 1? Oh, 32 out of 1,000, because it happened 32 times. How likely is it that I got a 2 out of a 2? Oh, 42 over 1,000, because it happened 42 times. Whatever your numbers are, you just divide them by 1,000. That gives you the bottom row. Does that make sense? Or we still have no idea what I'm talking about?
I just got really confused.
Can I try to clarify a little? I think I know what you're saying.
Please.
So,
I'll take a nap. This is great. Please go ahead.
So like basically, let's say there was 40 of us in this class, and if all of us flipped a coin at the same time and half of us got heads, then we would put 20 out of 40 for that first run. We got heads 20 times. Is that how it works? Or no?
Well, whatever. I mean,
not exactly.
Okay.
Because what you said is all of you flip a coin, but no, all of you are flipping 15 coins.
Yes.
Every one of you is flipping 15 coins. Okay? So if you flip 15 coins, you will get some number of heads between 0 and 15. Each one of you, correct?
but also that would only be one simulation, and we're trying to do 1,000, right?
Right.
So out of these 1,000
that's right.
times, we flip 15 coins.
Where did
then we
the
would
1,000
get.
from?
Oh, I made it up as a number. I just said randomly we do it 1,000 times. You want to do it 10,000 times? Do it 10,000 times. You want to do it 1,000,000 times? Do it 1,000,000 times. That's up to you. The more times you do it.
Well, on the test, though, would we get it like one?
No, you couldn't get this on a test because you can't run a simulation on a test.
Yeah. I think it would help if you explained it in terms of the 15 kindergarteners, because I think we're getting a little confused.
Yeah, that's where I got confused.
Oh, okay, so let's try it again. Let's try it again.
Well, there is 15 kindergartners. We're just
hold
trying
on.
to see how many boys are there.
Yeah, there are no kindergartners. They don't exist. Okay, there are no kindergartners. We're just imagining a class of kindergartners that don't actually exist. And that class that we're imagining is going to have some boys and some girls. Correct?
Mm-hmm.
But the class does not exist. It's a make-believe class. They don't exist anywhere in nature. We're trying to figure out how likely is it that this class is going to have 0 boys or 1 boy or 2 boys all the way through 15 boys. So what we do is we take 15 coins and we flip them. And after flipping these 15 coins, we count how many heads we have. So how many heads do you imagine that you just got when you flipped 15 coins? Give me a number.
Let's say 7.
Okay, so 7. So what you're going to do is you're going to put a little 1 in the 7 box. Not on the number 1, but you know how you do 1, 2, 3, 4, 5, and like a tally mark, right? You're going to put a tally mark by 7. Okay? And then you're going to collect your coins, and then you're going to do it again. What do you get this time?
2.
Okay, so you put a little tally mark by 2. And then you collect the coins, and you do it again. What do you get this time?
3.
Okay, you put a little tally mark by 3.
And we do that until we get to 1,000.
Yeah, unfortunately, all I can do on the thing is put the tally marks, but I can't really explain what's going on behind the scenes. I need you to close your eyes and imagine this is going on.
I think what I'm getting confused about the most is I understand the 1,000 simulations and the whole estimated probability, all that.
Yeah.
But the example itself is saying 15 kindergartners, and that has 5 girls and 10 boys. And so what are we exactly trying to figure?
5 girls and
are we looking at the class activity problem and then like trying to
Yeah, but I
Like,
haven't.
that's what my
Yeah, but
Go
I'm only on. Okay, you know what? It's already 8:15. So let me think of a way of doing this in a better way, because apparently this approach did not work. Let me see what I can figure out, and we'll pick up here again on Wednesday.
Possible to use visuals, because I think that's what we're all getting lost on. Is we need to be able to see it.
I understand what you're saying. I have to figure out a way to do this visually. So let me think about a way of doing that, and we'll start here again on Wednesday. Okay, so let's just pretend this last section didn't occur, and we'll pick up here again Wednesday, and I'll
Would it be easier to
try to
share
figure out a way
like
to-
share your screen with us, and you're having the
but I'm not writing anything. There's nothing to write. It's just you know, I can't make a little picture of me flipping a coin. I have to come up with a way of throwing out there what I'm doing in a visual way, and I'm drawing a blank right now. But give me 48 hours. I'll see. Or maybe tomorrow in class when I teach my other 211, maybe someone will say, "Oh, just do it this way," and I'm like, "Oh yeah, that works." I'm always learning like you're learning. Let me see what I can come up with, and we'll pick up here again Wednesday. Okay?
All right.
Okay.
Thank you.
So remember,
Thank you.
You're welcome. But remember, start the chapter 1 homework because we finished the chapter.
All right. Thank you, Professor.
I'm gonna stop sharing.
Yeah, thank you very much. Thank you.
Okay, bye guys.
Have a good day.
You
Listen,
too.
I have a question.